Hi, my name is Mark Wilde. I'm a professor at Louisiana State University, currently on sabbatical at Stanford for the calendar year from January to December. I started recording some of the lectures and seminars I've given in the past due to the coronavirus and the quarantine. I think it's a good opportunity to do this kind of thing and share work that was only shared with a limited audience and now share it with a wider audience on YouTube. This is a talk that I gave at SQuInT in 2019. SQuINT is a conference or workshop that's held every year, and it's organized by the Center for Quantum Information and Quantum Control at University of New Mexico. It's a nice opportunity for researchers in the U.S. to gather and discuss the latest work. It includes theorists and experimentalists. So what I talked about there was work that I did with Xin Wang. At the time, he was a postdoc at University of Maryland when we did this work, and then he later joined Baidu Research in Beijing. So this talk that I gave was about two works. One is something that I did as a single author. It's kind of a story with this work. And that summer, I was playing basketball and ruptured my Achilles tendon. And so I had to stay in bed for a month and a half. And without much to do, I spent a lot of time writing this paper. And as a consequence of that, I started communicating more with Xin, who I knew and who I met at some conferences. And then he had the idea of attacking this problem called exact entanglement cost. And so then we put our heads together and we wrote this paper that was on the archive. So, and that started a nice productive collaboration with Xin. Okay, so let's move on to the topic of the talk. It's this topic of entanglement cost, of preparing quantum states, and simulating quantum channels. Okay, so just a bit of a review. What is entanglement? What is not entanglement? Entanglement is usually defined by what it is not. And so let's start with that. A separable state is a state that has this form mathematically. So it's a convex combination of tensor product states. What does that mean physically? The state can only be prepared by what's called local operations in classical communication. So Alice and Bob are in distant laboratories, and they're allowed to call each other over the phone line, and they're allowed to do arbitrary quantum operations in their laboratories. We can assume that they have fault-tolerant quantum computers locally in their labs. So with such a set of operations, often abbreviated as LOCC, Alice could flip a coin or a multi-sided die, and based on the outcome, prepare a state rho IA. She could tell Bob the outcome I of the coin flip. That's called shared randomness, and she's communicating the randomness to Bob, who would then prepare rho IB in his lab. And then if they discard the outcome of the coin flip or the roll of the die, this is the state that describes that. So that's a separable state. And the point is that there was no quantum interaction needed to make this state. And so an entangled state is a state that's not separable. Okay, so this is kind of well-known stuff, but it's still worthwhile to review. And in entanglement theory, the natural set of free operations is what we discussed. So this is local operations in classical communication. Okay, so it's exactly that. And mathematically, these operations are difficult to deal with. For example, if you'd like to optimize over the set of LOCC channels, if you want to optimize some objective function, typically this is going to be computationally hard, and more precisely, it'll be NP hard. So LOCC operations are discussed in their mathematical structures discussed in a paper of Eric Chitzamber that was published in Communications of Mathematical Physics. And one guiding principle for entanglement theory is that you cannot use LOCC to create entanglement. Okay, so here in this picture, we see Mario and Luigi. This is, I guess, replacing Alice and Bob. And it's meant to depict local operations in classical communication, what they're allowed to do. Okay, so this paradigm of entanglement theory, I didn't include the reference here, but it was established in a famous paper of Bennett, DiVincenzo, Smolin, and Wooters in 1996. And it kind of created a whole way of thinking. And that's this resource theoretic way of thinking that's now inspired a whole bunch of areas, a whole bunch of different quantum resource theories. And there are even workshops on this topic now. Okay, so entanglement is very important. To do basic protocols in quantum information theory, the basic protocols are teleportation, dense coding. You need a unit of entanglement. You need one Bell state to do one teleportation. You need one Bell state to do one superdense coding protocol. And a Bell state is also called E-bit if you start thinking of quantifying entanglement in terms of bits. Entanglement is also useful in quantum cryptography. So there's entanglement-based protocols for quantum cryptography. This was started by Arthur Eckert in 1991, and it's inspired a whole line of thinking in terms of device-independent quantum key distribution. There's a whole rich literature on that topic. So entanglement is very important, and one thing we want to do from a fundamental perspective is quantify it. Okay, so that's one of the goals of entanglement theory. And there's an axiomatic approach, which is outlined here. So there are some basic axioms that you'd like for an entanglement measure to obey. The most basic one is this monotonicity under LOCC. So what does that mean? If you have an entanglement measure E, it's some function of a quantum state. You plug in the density operator description of the state to the function, and then you calculate it, and that's what this E rho is. It gives you a numerical value, typically greater than or equal to 0. So the most fundamental axiom is that if you apply an LOCC channel to the state of interest, then entanglement cannot increase. So that's somehow intuitive. If it were not the case, it would be kind of strange. Okay, another basic axiom is faithfulness. So, and you might even call this like strong faithfulness. So it's an if and only if. So if the state is separable, unentangled, the entanglement measure should take its lowest value of 0, and vice versa. So if the entanglement measure evaluates to 0, then that implies that the state is separable. Okay, so that's similar to like if in mathematics we study norms. You know, there's like a faithfulness criterion for norms of vectors or operators. There are other axioms that are desirable. One is convexity. Another is additivity. And then there's a more nuanced version of this LOCC monotonicity that's called strong monotonicity. And that's of interest also. So we'll get to this stuff a bit later in more detail. There's a large number of entanglement measures that are known now. There are some very nice reviews of entanglement measures. One is a review article by Martin Planio and Shashank Vermani, published in 2007. And then Matthias Christendel's PhD thesis is an excellent resource as well. It kind of guides you through the theory of entanglement. So what I talked about here was the axiomatic approach. There's also the operational approach or information theoretic approach. So you think of a task of interest, and then you're interested in like the optimal rate at which the task can be conducted. And so there are operational entanglement measures that arise from this line of thinking as well. And the famous ones are distillable entanglement and entanglement cost. So distillable entanglement is if you're given a large number of copies of a state row AB, you're allowed to do LOCC on it, you want to distill from the many copies of the mixed state, in general it could be mixed, you want to distill as many Bell states as possible. Why you're interested in Bell states? Because those can be used for faithful teleportation or superintense coding or secret key extraction. Okay, so that's distillation. The reverse task is entanglement cost, and that's what we're interested in this talk. That's the main topic. So entanglement cost is what is the minimal number of Bell states or EBITs that you can use along with LOCC to prepare some number of copies of row AB. Okay, so that's the main thing of interest, and we'll talk about it in detail in the forthcoming slides. Okay, so indeed, this is what I was talking about, entanglement cost. This was introduced by Bennett et al. In this famous BDSW paper that I mentioned previously. And this quantifies the minimal rate of converting little r times little n copies of a Bell state to n copies of a target state of interest. And then you for any finite number n, you allow for some wiggle room or some tolerance. You don't demand that it's done with perfect fidelity. What you do demand is that in the limit of large n, the fidelity tends to 1. Okay, and so you're interested in the rate. And this kind of task is, it's the way that this is defined is motivated by, if you study works of Shannon in classical information theory, it's the same kind of thinking. If you open up some classical information theory textbooks, like the famous Cover and Thomas textbook. Okay, so what is known for this? There's a nice result of Patrick Hayden, Michal Horodecki, and Barbara Terhall. Now we're at the 20th anniversary of that result. They proved that the entanglement cost is equal to a quantity called regularized entanglement of formation. So entanglement of formation is a notion, it's an entanglement measure that was defined in this paper based on the concept of entanglement cost. But you know, in this original paper, they didn't prove that the entanglement cost itself is equal to entanglement of formation. And this later work showed that if you do a procedure called regularization, then indeed the entanglement cost is equal to the regularized entanglement formation. So the regularized entanglement formation is difficult to compute in practice. So if you were to try to write a computer program to do this, it's actually not clear whether entanglement cost is even computable in the computer science Turing sense. That's an interesting open problem. And this kind of problem plagues much of quantum information theory when you have these regularized expressions. If the regularization is not necessary, if in fact the entanglement cost is equal to entanglement formation, that simplifies the task, but it's actually still in general NP hard to compute the entanglement formation. So it's a formidable task to compute these operational entanglement measures, and it might even be impossible. You know, it might be as hard as the halting problem in computer science. Okay, so that's a bit of a spiel about entanglement cost. Let's talk about distillable entanglement. This is what I was mentioning on the previous slide. Now we have a figure. So with distillation, it's the reverse of this. You start with n copies of the state rho depicted here. You allow it to do LOCC, and you're trying to extract as many E-bits as possible with high fidelity. And it's the same kind of thing. You want the fidelity to become arbitrarily large, and the limit, you want the fidelity to become arbitrarily close to 1 in the limit of large n. And the distillable entanglement also is difficult to compute, and it may very well be uncomputable. So there are, you know, in light of the situation, your next best thing to do is to try to bound the quantity, to at least get some handle on it, and to say, oh, you know, there's a scheme in principle that exists that could do entanglement distillation at such and such rate. That would be a lower bound on distillable entanglement. We're also interested in impossibility statements. You know, the distillable entanglement cannot be larger than a certain amount. And then that would tell you, like, oh, I can never hope to exceed that amount. And so that kind of result has appeared, these kind of impossibility results, or in the information theory language, they're called converse bounds. So the relative entropy of entanglement is an entanglement measure, and that's known to be an upper bound on distillable entanglement. There's a refinement of that I didn't list here. It's called the Raines relative entropy. Rain is like rain from the sky. The person's name is Eric Raines. And he came up with a modification of relative entropy of entanglement that was quite clever. And he proved that it's a better upper bound in general on distillable entanglement. Another bound that's incommensurate with relative entropy of entanglement is called squash entanglement. This came later. It was discovered by Matthias Christendal, Andreas Winter. You should also look at papers of Bob Tucci. You can look at the Wikipedia page to see some of the history of squash entanglement. The squash entanglement is inspired by a concept in classical information theory called intrinsic information. This was invented by Ueli Maurer, that's M-A-U-R-E-R. And, you know, Ueli Maurer is a professor at ETH Zurich. Matthias Christendal did his diploma thesis there. And if you sort of track the history of it, he was working with Maurer and maybe even Renato Renner during his diploma thesis. And eventually, some years later, he collaborated with Andreas Winter, and they realized, oh, we can have a fully quantum version of intrinsic information, and they called it squash entanglement. Okay, so given all this history, there's now a question that comes to the forefront. We said there's entanglement cost with LOCC, there's distillable entanglement with LOCC. These are hard to compute, if not uncomputable. And so that leaves us with the question, is there some entanglement measure that is easy to compute and has a clear information theoretic meaning? So that's the question that we addressed in this work. And indeed, the answer is yes. Yes, there is. So this is one of the first results that I'll talk about in this talk. And that's this entanglement measure called kappa entanglement. Here we were following a tradition of Xin when he invents a new information measure or entanglement measure. Typically assigns a Greek letter to it, and so we just went with kappa for this. In a later paper, we showed that this can be interpreted as the max logarithmic negativity. So logarithmic negativity is a very famous entanglement measure. And then we showed how this one is related to that. And there's actually a family of logarithmic negativity entanglement measures. So what is going on with this entanglement measure? You look at it, you might wonder, well, what is this about? So you take the state rho AB, you have the density operator description. It's a matrix, and you can imagine like writing up this matrix in MATLAB, for example, on your computer. Okay, so you plug it in, and then you do an operation called the partial transpose, and I'll talk about what that is on a future slide. And then you look at all matrices or operators that are positive semi-definite. And furthermore, when you take the partial transpose, this operator inequality is satisfied as well as this one. These operator inequalities are common in the mathematical study of quantum information theory. What it means is that if I take this matrix and I subtract from it this one, the rho AB partial transpose, then that matrix is positive semi-definite, or all the eigenvalues are positive. Okay, so that's what it means. And one thing you can infer from this is it's written explicitly that S should be positive semi-definite, but if you inspect this, you can see that S, the partial transpose of S is greater than the negative of the partial transpose of S. You can bring this over to the other side. You see that twice the partial transpose of S is greater than 0 in the operator inequality sense. So that means that the partial transpose of S is also positive semi-definite. Okay, so you look for all S that satisfy this, and then you want to minimize the trace. Okay, so it turns out that these constraints are semi-definite constraints. You know, we're writing them as operator inequalities. And this can be solved efficiently. You know, if you want to find the optimal value, it can be solved efficiently by using semi-definite program. This can be done in MATLAB using a package called CVX that was invented by people at Stanford. It's a free package you can use, so if you have MATLAB, you can use it. And I say efficiently solvable, we should be careful with what that means. That means that the complexity of the algorithm, the runtime, is polynomial in the dimension of the density operator, okay? So that's the statement. Now, if you think about qubits, suppose we have the state rho AB consists of n qubits. That means the runtime will be polynomial in 2 to the n. So, you know, if you're thinking of efficiency in terms of number of qubits, then it's not efficient. So it's important to clarify that point. Okay. Semi-definite programming is something that's used quite widely in quantum information these days, and so it's worthwhile to invest some time and learn it. If you look at notes of John Watrous, it's explained very well. Okay, so what do we show in this work? The kappa entanglement is precisely equal to an operational quantity that we call exact entanglement cost under PBT operations. Okay, and then I wrote here the words resource theory of NPT entanglement. We should clarify what that means. I think we do clarify a bit. Okay, so let's just mention what it means now. We talked about resource theory of entanglement where the free operations are LOCC. We said how LOCC is hard to work with mathematically. So then what we can do is we can enlarge the set of LOCC channels to something called PPT channels. More precisely, we should probably call them channels that completely preserve the positivity of the partial transpose. And so in other papers, if you look at other papers, we call it C-PPT-P. But for simplicity, we'll call it PPT operations. So what you do is you expand the set of LOCC to these PPT operations, and then those are the free operations. The free states are the ones that are called PPT states. And so the ones that are resourceful are states that don't have a positive partial transpose. And so those are called negative partial transpose states, or for short, NPT. So that's kind of an explanation of what's going on here. Okay, so what we're doing is we're changing the entanglement cost problem to be about PPT operations instead of LOCC. So it's a simplification that we're doing. It's following the spirit of Eric Raines's paper from the late 90s, early 2000s. And we can show that this entanglement measure obeys all kinds of nice properties. So it obeys it's monotone under PPT operations. Since that includes LOCC, it's monotone under LOCC operations. So it obeys the most important axiom for entanglement theory. It's also additive. So that means if you take n copies of the state rho AB and evaluate kappa entanglement, that will be equal to n times the kappa entanglement of a single copy of rho AB. So that's a very nice property. And that's one of the main reasons that we're able to establish this theorem, okay? It's normalized. What does that mean? If you evaluate it on a maximally entangled state of Schmidt rank D, it'll evaluate to log of D, the binary logarithm of D. I didn't write it here, but this logarithm should be understood as a binary logarithm so that the units of entanglement are E-bits, which is short for entangled bits. It's also faithful. So that's what we talked about earlier. It's faithful on PPT states. So it's equal to 0 if and only if the state is a PPT state. Okay, so what is the task of exact entanglement cost? Mathematically, it's written like this. In plain English, it's this. What is the minimum number of copies of an E-bit? What is the minimum rate at which we need E-bits to generate n copies of the target state, rho AB? And the free operations can be LOCC, or we can enlarge them to PPT. So this is an exact entanglement cost. Previously, we were talking about the Hayden et al. Result. That was more like the Shannon style entanglement cost, where you allow for a slight error for any finite n, but you demand that the error goes to 0 as n gets large. Here, we're not doing that. We demand that the conversion is always exact, okay? This right here is what you can call the one-shot exact entanglement cost. So it's just for a single copy of rho AB. What is the minimum number of E-bits that you need? So if you look at this formula, we're taking a minimization over the free operations. We're trying to minimize the number of E-bits. That's the log of the Schmidt rank of this maximally entangled state. And then we're acting on the maximally entangled state with a free operation. In this talk, it's LOCC or PPT. And then you want to make this target state rho AB exactly, okay? So something to think about is, like a basic thing that you could do. So what is a very basic thing that you could do? Alice could start and make rho AB locally, okay? And then if she shares a maximally entangled state, let's say where the dimension D is the same as the dimension of B, then she could do teleportation. Her and Bob could do teleportation, right? So the Bell measurement, the classical communication, that is an LOCC, right? So in teleportation, you have already LOCC going on. So with that, the exact entanglement cost is no larger than the dimension of B, okay? And sorry, is no larger than the number of qubits in B, so the log of the dimension, okay? And then by a symmetric argument, we could have Bob make rho AB and then teleport A to Alice. And so then you see that the one-shot exact entanglement cost is no larger than the log of the minimum of the dimensions of A and B. So that's a simple thing you can do, but in general, you can do better. You know, if the state's pretty mixed, maybe there's not much entanglement in it, and so you would need far fewer EBITs to generate it. Okay, so that's the one-shot exact entanglement cost. The exact entanglement cost is, maybe more properly, we should call it the asymptotic exact entanglement cost. It's just where you take a limit of this. This should actually be a lim sup. That's a mistake that we corrected later. Okay, so it's, you know, you plug into this formula, this optimization task, rho AB tensor n, and then you're interested in a rate, so you divide by n. And so that's the minimal rate at which you need EBITs to make the state rho AB tensor n exactly. Okay, so that's the exact entanglement cost. If the free operations are LOCC, then it's difficult to calculate this quantity. You know, there's some prior work of Barbara Terhall and Michal Horodecki on that. And even for simple states, this quantity is not known. Okay, so that motivates going in a different direction, and that's the direction that we took. Let's follow Eric Rains and let's think about the partial transpose. So what is that? If you study entanglement theory, this is one of the first things that you learn. So we can represent an operator in terms of a basis of operators. A simple one is just to use this kind of expansion of, you know, orthonormal bases for the Hilbert space for Alice and orthonormal bases for the Hilbert space for Bob. And then when you make a Kettner bra like this, that'll be a basis for the space of operators on A and B. Okay? And when you do the partial transpose, it amounts to just flipping these indices. The partial transpose is basis dependent, unlike the Hermitian conjugate. So it's with respect to a given basis. That's somehow important mathematically. A state is said to be positive partial transpose if, when you apply the partial transpose operation, to be clear, you know, to apply this to a general operator, it extends by linearity. So you would take the rho AB, you'd expand it in this basis, there'd be some coefficients, and then you do the partial transpose on each term in the sum. Okay, so that tells you how to do the partial transpose in general. And a state is said to be positive partial transpose, or PPT, if this operator inequality is satisfied. And it's exactly what it says. When you take the partial transpose, the operator is still positive semi-definite. Why is that interesting or relevant? For a separable state that we talked about earlier, I think it's worthwhile to go back. If you look at this, if you do the partial transpose on the B system, it's a linear operation. And so each of these terms in the sum will get a partial transpose. Well, sorry, each of these terms in the sum on the right side will be transposed. And if you take a density operator and you take its transpose, then it's still a legitimate density operator. So for a separable state, it's always PPT. So that's the key insight. For an entangled state, when you take the partial transpose, it need not be the case. If you take the partial transpose of a Bell state, then the resulting operator is proportional to a unitary swap operator, and that has negative eigenvalues. Okay. So we're going beyond separable states, we're going beyond LOCC, then we're looking at these PPT operations. Okay, so that's a bipartite quantum channel such that when you first do the partial transpose on B, then you do the channel, then you do the partial transpose on B prime, that channel, that map is still completely positive, okay? If you don't know what completely positive is, it's worthwhile to pause the video and do some Google searches. It's in various textbooks on quantum information theory. Okay, so the key thing from a resource theoretic perspective is that if there's a channel that satisfies this property and it acts on a PPT state, the resulting state is still PPT. So the free operations preserve the free states, which is like the basic thing that you need in any resource theory. So this concept of PPT states and channels, it has applications across the board in quantum information theory. Okay, so we're interested in the exact entanglement cost problem. If we expand the LOCC operations to PPT operations, when those are free, previous bounds for the exact asymptotic entanglement cost were established in this work of Konrad Oudenaarde, Martin Planio, and Jens Eisert. That was a physical review letters paper. You can find it on the archive by searching for the intersection of their names. This bound was not known to be tight in general, okay? And it was only tight for particular states such as 2-qubit states. So that was nice to have it for some examples, but we want it in general. Okay. The other thing to realize is this inequality. This follows pretty directly from the definitions. So let's go back to the definition. Right. So if we choose the free operations to be LOCC, there's going to be a certain value, and we're minimizing over those. If we choose the operations to be PPT, that includes LOCC. So the minimum value can only be the same or smaller than what you get with LOCC. And that will extend to the asymptotic measure. And so that allows you to conclude this inequality pretty immediately. Okay, so this was the main result that I mentioned earlier. The exact entanglement cost is equal to the kappa entanglement. So how do we arrive at this result? To give you some sense of it, we can write the one-shot exact entanglement cost as this optimization, where sigma is a state. This is not a semi-definite program. I suppose you'd call this like bilinear and maybe even integer program. I'm not sure about that. But the point is that M is an integer. And the fact that you have m plus 1, m minus 1, that's multiplying sigma. It's not easy to solve this. It's not a semi-definite program, right? So that's what we're saying here. So it's just hard to calculate it exactly. But what we do instead is we bound it. Okay, so this is a depiction of a sandwich, and the point is that we're sandwiching the quantity of interest, the PPT exact entanglement cost, by an upper bound involving cap entanglement, by a lower bound involving cap entanglement, and that's what's shown here. Xin did this as he made this figure. He visited Louisiana, and at some point we went for shrimp po' boys. They're very tasty. It's a common dish in Louisiana. Po' boy is short for poor boy. It was a sandwich intended for like a working person in Louisiana, but it eventually became very popular. And there's some places it can be quite expensive. So it's not really, the name is there, po' boy, but it's not really intended for a poor boy. And there are many places in New Orleans and Baton Rouge to get some tasty po' boys. And me personally, I like the shrimp po' boy the best. Okay, so we have these the sandwich bound for the exact entanglement cost. Okay, for the one-shot exact entanglement cost. So then we can use the fact that the cap entanglement is additive. That's a separate thing we need to do. To prove that, you use the duality theory of semi-definite programming. That's a whole story on its own that you can learn from the notes of John Watrous or his book. So you apply the definition of the asymptotic exact entanglement cost. You use the bound for the one-shot quantity to get from this first line to the second line. You use the additivity, right? And then once you have that, you're done. You take the limit, and what'll be left after you take this limit is the exact the cap entanglement. And again, this should be lim sup. That's a minor typo. Okay, and then by a similar kind of idea, you get a lower bound. So then what happens is that for the one-shot exact entanglement cost, you don't have it precisely, but then in the asymptotic limit, these -1, +1, it washes away. And we're left with this nice result. So that's one of the main results of this work, is that if you simplify entanglement theory to allow for PPT operations, and you think about exact entanglement cost, you get this very nice equality. So that's the sense in which E kappa has an operational or information theoretic meaning. And it's also efficiently computable by a semi-definite program. So as far as we're aware, this is the first example in entanglement theory of an entanglement measure that has a precise information theoretic meaning while being efficiently computable. So it's highly desirable. Okay. So there are other properties of the exact entanglement cost that we can deduce from the cap entanglement. One is that this is a simple observation. Since the cap entanglement is additive, that implies that the exact entanglement cost is additive also. That's not necessarily the case for entanglement measures in general. There can be superadditivity effects, and in some cases, superactivation effects. Okay. So, but that doesn't happen for the PPT exact entanglement cost. The other thing that happens is that the exact entanglement cost violates convexity. So what does that mean? Convexity would be the statement that in general, the mixture of two bipartite quantum states does not exceed the average value of the individual entanglements. Okay, but what we find is that the convexity can be violated. Why is that significant? It's often thought that entanglement measures should be convex because, often convexity is associated to decrease of entanglement under the loss of classical information that describes the state. But that's only true for certain entanglement measures that correspondence is precise. So the fact that the exact entanglement cost violates convexity, it suggests that maybe convexity actually is not that important a requirement for an entanglement measure, because here we have a precise information theoretic task, and yet the optimal value violates convexity. Okay. The other thing about exact entanglement cost is that it violates something called monogamy of entanglement. So the most extreme form of entanglement monogamy is that if two qubits shared by Alice and Bob are maximally entangled and in a pure state, that implies they can't be correlated at all. They're just in a product state with any third qubit or any other quantum system for that matter. So that itself is captured by this inequality. What would it mean here that the entanglement of rho AB would be like the number of E bits in the maximally entangled state. The E rho AC, if there's no correlations between A and C, that would evaluate to 0. And then that cannot exceed the entanglement between Alice and then we consider Bob Charlie as a single system. So in this case, the entanglement of rho ABC would also be equal to the number of E bits. So the monogamy inequality is satisfied for that simple example. More generally, you can have trade-offs between the amount of entanglement with Alice and Bob. But the monogamy, if it holds, it says that the total entanglement between Alice and Bob and Alice and Charlie cannot exceed the entanglement if you consider Bob and Charlie together as a single system. Okay, so monogamy was thought to be something essential for entanglement. That has been debated in the literature previously. There's papers of Gilad Gore about that. But what we find is for the PPT exact entanglement cost, the monogamy is violated, and the simple example illustrates it. Okay, so now we're going to move on to a new topic, sort of expanding the scope a bit to quantum channels, and we're going to consider entanglement cost when trying to simulate quantum channels. Why is that interesting or relevant? In general, a quantum channel can have the ability to preserve quantum information. Okay, so let's say that there's a satellite link that connects one satellite to another in outer space, like around in the orbit of Earth. So that's going to be a pretty good link for sending quantum information, because there's not much loss along the way, other than the loss that occurs simply from propagating an optical mode in free space. The vacuum has a role in that. So such a link can preserve quantum information, and it can be used to establish entanglement. Okay. So if it can do that, that means it's a good quantum channel. And you could ask, like, using that lossy quantum channel, what's the rate at which we can extract EBITs? That would be the distillable entanglement of the channel. So just as we did for states, we can flip the question around and we can say, well, if that channel has some ability to create entanglement, that means that if we'd like to simulate it, then there would be some cost of entanglement required to do so. So it's like we're flipping the question around, just as we did for states. Okay, so that's the idea of entanglement cost of quantum channels. That concept was introduced by Mario Berta and his colleagues. I believe it was a paper of Berta, Stephanie Vayner, Fernando Brandau, and Matthias Christendahl. And I think they called the paper Entanglement Cost of Quantum Channels. So here we're extending those ideas to some different scenarios. So let's get a bit more precise. What do we mean by entanglement cost of quantum channels? So quantum channel is a link from Alice to Bob. It's described by a completely positive and trace preserving map mathematically. If you're coming from classical information theory, it's a generalization of a classical channel. It's a generalization of a conditional probability distribution. So in the channel simulation task, the entanglement cost channel simulation task, we're interested in supplying Alice and Bob with some Bell states. And then this A system is like the channel input. And then we want to do a free operation, so either an LOCC or a PPT channel on the channel input on their shares of the EBITs. And then the whole process would output a B system. And we want it to be such that if you were to draw a box around everything going on inside here, and all you could access is the input port and the output port, no one would be able to tell any difference between this procedure and the original channel. So that's what we mean by channel simulation. Okay. And you can play around with it. You can try to do exact channel simulation, or you can allow for a slight error. Okay. So the simplest kind of channel simulation is quantum teleportation. So by using a single EBIT and 2 classical bits, you can exactly simulate a noiseless qubit channel. That's what teleportation does. So then if we make classical communication free, this is the paper I was mentioning, this group of authors introduced the entanglement cost of a quantum channel. So what they're demanding is that there's a desired channel that you'd like to simulate. So this is the ideal channel you'd like to simulate, and you allow for n copies. Again, it's going to be an asymptotic kind of thing. And you allow for EBITs at a rate of R, okay? And you allow for a free operation, like in this diagram, acting on the channel input and the shares of the EBITs. And then you minimize what's called diamond norm. If you don't know diamond norm, you should pause the video and look that up. It's in some standard textbooks. And you can just think of it as a distinguishability measure or a distance measure for quantum channels. It has a very good operational meaning, which is, convincing for why we should use it in quantum information theory. So the point is that they demand that the error, you can think of the diamond norm as quantifying the error of the simulation. So we want that error to vanish in the limit as the number of channels that you're trying to simulate becomes large. And then we're looking for the minimum rate at which you can do this simulation. So that's the operational formulation of entanglement cost. Later we realized that this is a parallel simulation because you're trying to simulate a tensor product channel. So we'll return to that point in a bit. What they proved is a formal mathematical expression for the entanglement cost of a quantum channel. This generalizes the results of Hayden et al. That I mentioned earlier on for the entanglement cost of quantum states. So what does this mean? You take an input to the channel. This input is actually a bipartite input. You act on some of the shares of this state with the channel. So then that makes a bipartite state. You calculate the entanglement of formation. You divide by n, that's the regularization. And then you maximize this value with respect to all input states. So this is a channel generalization of regularized entanglement formation. And then you take the limit as n goes to infinity. So that's the formal mathematical expression. In general, it's hard to calculate, but for certain channels, it simplifies. And so that was, they looked at some examples in their paper, but another contribution of the paper I wrote in 2018 computed this for, showed how this could be calculated for more examples of channels. Okay, so now this is the one-shot entanglement, exact entanglement cost. So we allow for free operations that are either LOCC or PPT. And previously we were talking about we allowed for an approximation error, but that it had to vanish as n becomes large. Now we're demanding more, that the simulation has to be exact no matter what. So here we're trying to find the minimum number of EBITs that you need, allowing for a free operation, LOCC or PPT, to act on the channel input. This right here is depicted in this diagram. The P should be lambda. And this is the channel input, this is the channel output. And you want that this channel is the same as the desired one you're trying to simulate. And you want to minimize the rate at which you need EBITs to do this. Okay, so one way to make this an asymptotic notion is to simply plug in parallel uses of the channel. Okay, so that's what that means. And big N tensor little n is little n parallel uses of the channel big N. Okay, and again, this should be a limb soup. Okay, so what can we say about this? If we allow the PPT operations for free, the one-shot exact entanglement cost can be written as this optimization. If you look back to what we had, let me go back. Yes, it was right here. This is the one-shot characterization. This is how you can write the one-shot exact entanglement cost as an optimization. So that's what it is for states. Then what we're showing now is a channel generalization of that. Okay, so what is going on here? This is the Choi operator of the channel. The Choi operator is proportional to the channel acting on one share of a maximum entangled state. It can be, if you don't know what Choi operator is, it can be worthwhile to pause the video here and look that up a bit. Okay, so what we're doing is we're taking the partial transpose and then we're doing these operator inequality comparisons. Q has to satisfy these two constraints. It has to be positive semi-definite, and when you trace over B, that has to be the identity matrix. Okay, so that means that this Q itself is the Choi operator for a quantum channel. These two constraints are satisfied for any Choi operator of a quantum channel. Okay, so similar to the situation for states, this is also difficult to compute. Okay, but what we can do is similar to what we did for states, we can get these a sandwiched approximation. Okay, so we can define the kappa entanglement of a quantum channel, and this is a pretty direct generalization of the state concept. You know, for the state, for the kappa entanglement of a quantum state, there was an S operator that actually satisfied, you know, these inequalities were demanded of it. But now what changes is the objective function. So the objective function is you take the partial trace and then the infinity norm. And, you know, it has to do with the fact that this is a channel quantity. We have to optimize over inputs to the channel. That's kind of what's playing a role with this infinity norm. Okay, so our second result is that the exact entanglement parallel entanglement cost is equal to the kappa entanglement. So it's a similar kind of idea. You use the sandwiched approximation. You can use SDP duality to show that this kappa entanglement of a channel is additive. And you combine those and you get this result. So the exact parallel entanglement cost is equal to its kappa entanglement. So again, you know, this is like a step higher up in the hierarchy. We're going from states to channels. And this shows that the kappa entanglement of a channel has a direct information theoretic meaning, and it's efficiently computable. I didn't say that here, but this quantity is computable by a semi-definite program as well, just like the kappa entanglement of states. Okay, so one thing that's very nice is we define the kappa entanglement of a channel like this. You can actually show that it's equal to an optimized version of the kappa entanglement of quantum states. So you send in one share of a state to the channel, you get a bipartite state shared between Alice and Bob, and you evaluate its kappa entanglement. Then you just optimize over all possible input states. And that gives a maybe more intuitive notion of what the kappa entanglement of a quantum channel is. There are some axioms that you know, just as we had axioms that are desirable for a state entanglement measure, there are axioms that are desirable for a entanglement quantifier for channels. Okay, and so we talk about those here. One is that it's monotone to the action of what's called a super channel that's PPT. I don't think I get into that here, so I won't mention more about that, but that's basically a generalization of LOCC monotonicity. Another nice property is that it's additive for quantum channels. So if I plug in a tensor product of quantum channels to the kappa entanglement, that entanglement is equal to the sum of the individual entanglements. It's normalized, so the identity channel of dimension D, that has the ability to generate maximally entangled states of Schmidt rank D. So it's kind of intuitive that its entanglement should be equal to log D because it has that entanglement generation capability. And what this is saying is that the cost of simulating the identity channel is equal to log D. And that tells you that for the identity channel, indeed, teleportation is an optimal procedure to simulate the identity channel. It's also faithful, so it's equal to 0 if and only if the channel N is a PPT channel. And we said earlier that means, you know, completely preserves the positivity of the partial transpose. It also obeys something that we call an amortization inequality. Later on, this was called chain rule. What is the meaning of this? You can imagine that before using the channel, Alice and Bob share some generic state. Okay, so A prime is like some memory, it's some register that Alice possesses. A is the channel input system, and B prime is some quantum system that Bob possesses. So that state, you can send in the A system to the channel, and then you get this state. And so what this is saying is that the net entanglement, the net kappa entanglement that can be made with the channel is no larger than the kappa entanglement of the channel, right? So in this procedure here, there's the input system, there's nothing for Bob, right? So what this is saying, what this inequality is saying is that there's no gain by allowing the input state to have something for Bob, okay? So this is actually a very important concept for the sequential simulation of quantum channels, which is something we'll get to next. So what do I mean by this? Earlier we talked about a parallel simulation. Now we're going to talk about a sequential simulation. So the point is that you want to simulate the channels one after another rather than all at the same time. And someone could check how well these channels are being simulated. So, you know, to this port, there could be an input. To this output port, there could be a processing. And then the same for this output port. And so the point is that someone who's like checking how good the simulation is should not be able to tell the difference between the ideal realization of the channels in a sequential way and the simulation, okay? So this is the ideal thing that you want, the channels themselves. This is the simulation. So what happens is that Alice and Bob start out with some entanglement that they'll use to simulate the channel. There's the input to the simulation of the first channel. There's a processing by a free operation. This could be LOCC or PPT. Then you output the first channel use from the simulation. And then these memory registers are passed along to the next round. And then you keep doing this over and over again. And what we demand is that it's an exact simulation. It would be impossible to tell the difference between this process and this one if you were to plug in whatever way. And so that's what's depicted on this slide. These input states and these in-between processings are what someone could use to try to tell the difference between the ideal three uses of the original channel and the simulation. Okay, so that's the main idea. And a simulation code consists of you're using an entangled state of Schmidt rank M and this set of operations that are part of the simulation. And these are required to be the LOCC channels or the PPT channels. Okay, so this is the most general paradigm for quantum channel simulation, at least when you have IID uses of the channel that you're trying to simulate. It's tougher to do a sequential simulation than it is to do a parallel simulation. So it could potentially cost more in terms of entanglement to do a sequential simulation than it would to do a parallel simulation. That's what I'm saying right here. Okay. Nevertheless, one of the key results we can show is that the exact entanglement cost for sequential simulation is also equal to the cap entanglement. So that was a very interesting observation to make, at least for me, that the cost of the parallel simulation and the sequential simulation are the same, and both of them are given by the cap entanglement. I didn't expect that beforehand, but it was nice that it worked out. So how do we show it? The lower bound comes about because the cost of a sequential simulation is larger than the cost of a parallel simulation. And then we already had this lower bound for the cost of a parallel simulation. The upper bound is something different. And how did we show it? We need to come up with a protocol to realize a sequential simulation. So what was the basic idea for the protocol? You start out with some maximum entangled state, and then you demand that this procedure, it simulates the first channel exactly, and then it also outputs as many, as large a maximum entangled state as possible, and an exact maximum entangled state. And so then you just keep repeating this process where you simulate the channel and then you produce maximum entangled states. And so you need to have as many maximum entangled states such that you can keep doing this over and over again for n times. Okay. And then if you do a careful analysis of the resource cost, what you find is that this is an upper bound on the resource cost of a sequential channel simulation. And then if you take, if you divide this by n and take the limit as n goes to infinity, you again find that both sides of the inequality simplify to the kappa entanglement of a quantum channel. Okay. The next result is this notion of a resource seizable channel. And this is actually going back to, now we're switching gears from exact entanglement cost to approximate entanglement cost. Okay. But we are thinking in terms of the sequential setting of channel simulation. So there's a concept that that was introduced in this paper that I wrote. I called it resource seizable. Okay, so what does it mean? Let's step back a bit. We say that a channel is teleportation simulable with associated resource state if the channel can be simulated exactly by the action of an LOCC on the channel input and the resource state. Okay? Any channel is teleportation simulable with the maximally entangled state of sufficient Schmidt rank. And so this concept of teleportation simulable is like, well, if I can find a state that's not as good, it's more mixed in the maximum entangled state, then it could be a cheaper way to simulate the channel. Okay, so that's teleportation simulable. Resource seizable is if, in addition to being teleportation simulable, it's also possible to extract the resource state by free operations. So what do I mean by that? You would send in a separable state to the channel, you'd act with the channel, then you'd process it with the LOCC channel. And if by such a general processing of the channel by free operations, you can extract the underlying resource state, then the channel is called resource seizable. Why is that important? Well, it leads to a simplification. So the theorem that you can arrive at is that for these resource seizable channels, the entanglement cost with a general sequential simulation or with a parallel simulation, they're equal, and they're equal to the entanglement cost of the underlying resource state. So that was an interesting observation. And then the problem gets reduced to computing the entanglement cost of the resource state, which itself could be a formidable problem, as we discussed. But that's the main concept, that you can reduce the channel problem to a state problem for these special channels. And there are a lot of interesting channels that satisfy this property of resource seizability. So here are some examples, and I don't think I'm going to go into so much detail, but the basic channels that are resource seizable are the erasure channel, a dephasing channel, and a depolarizing channel. And what this is showing is that for the erasure channel, because it's resource seizable, we can compute its exact, the entanglement cost under sequential and parallel simulations. We can compute the exact PPT entanglement cost in analytical expression. For the dephasing channel, it's the same story. We get an analytic expression. We get an analytic expression for the exact PPT entanglement cost. For the depolarizing channel, it is resource seizable, but the underlying resource state is an isotropic state. And for that state, the entanglement cost is not known. But we can compute an analytical expression for the exact PPT entanglement cost. Another very interesting class of channels for practical applications are bosonic channels. So for several single mode bosonic channels, we get exact expressions for the entanglement cost and the exact PPT entanglement cost. And here's an illustration. Let's see. Okay, so this is the qubit dephasing channel. And what are we plotting? We're plotting the rate versus the noise parameter. Okay. So we see that this is the distillable entanglement. That's a result that was known. The entanglement cost of this channel, this was a new contribution. And the exact PPT entanglement cost is even above that. Okay, so it shows you for some examples. And it's worthwhile to reflect on different values. If Q is 0, it's the identity channel. So all the values coincide, and it requires one EBIT to simulate one use of the identity channel. The other extreme is when Q is 1, then it's the unitary sigma Z. And it's effectively an identity channel because you assume that it's known that a Z is being applied. So you can just undo it at the input or the output of the channel. And for that case, it's one EBIT to simulate one channel use. You then go down and down because it's kind of like the entanglement in the channel, or the entanglement that's required to simulate the channel, or the entanglement that can be extracted from the channel. It all goes down. And at Q equals a half, the channel is fully entanglement breaking. It has no ability to generate entanglement, and there's no cost to simulate the channel with free operations, because all it can produce is separable states. Okay, so that's kind of what's going on. Another important point to emphasize is that you see that there's a gap between distillable entanglement and entanglement cost. That means that the resource theory of entanglement for this class of channels is irreversible. So let's say that you're considering a dephasing channel with dephasing parameter of 0.2. Then you could distill entanglement at this rate. But that rate is not enough to simulate the channel, right? So it's not like you can go back and forth, extract EBITs, use them to simulate the channel, extract them again. There's going to be a loss in that process. So the resource theory of entanglement is irreversible for this class of channels, and that means in general it's irreversible. Okay. For Gaussian channels, we also have a kind of similar story. We can get an exact expression for the entanglement cost of this channel. It's given by this analytical expression. And the distillable entanglement of a pure loss channel is known. I should say a few words about what a pure loss channel is. This is a very basic model of photon loss that can occur in fiber optic communication or free space communication. It's a common model. Eta is the transmissivity of the channel, so it indicates the fraction of photons that make it from the input to the output on average. The common model used is this channel is just a beam splitter. So at one input port of the beam splitter, that's the actual input to the channel. At another input port, it's the vacuum state. That's this environment that I'm talking about here. And then one output port of the beam splitter goes to the receiver. The other output port is lost to the environment. So that's the pure loss channel. It's a very important model, and so it's gotten studied quite a bit in the literature. So what you can show here is as eta, the transmissivity approaches 1, the entanglement of the channel is increasing, both the distillable entanglement and the entanglement cost. And as eta goes to 1, if there's no energy constraint on the channel, then these two values will approach infinity, because I've described the channel here in the Heisenberg picture, but the channel actually acts on an infinite dimensional Hilbert space. And so if there's no energy constraint imposed on the channel, and the transmissivity, if it's a perfect channel, then it can be used to create an infinite amount of entanglement. Okay, but it's interesting that as soon as eta is strictly less than 1, then the channel, these values of entanglement cost and distillable entanglement become finite. And there's a similar story with irreversibility. So, there's a gap between the distillable entanglement and the entanglement cost. That means that the resource theory of entanglement for this channel is irreversible. Okay, that's really all I had to say. I guess it was quite a lot. The first part of the talk was talking about kappa entanglement of a quantum state. What were the main findings? It's efficiently computable by semi-definite programming. there was a particular sense in which it's efficiently computable. So it's the runtime of an algorithm to compute it is polynomial in the dimension of the state. It has a information theoretic meaning as an exact entanglement cost under these PPT operations. We then generalized this notion of kappa entanglement of a state to kappa entanglement of a channel that is also efficiently computable by semi-definite programming. Not only is this the exact entanglement cost of a parallel simulation, it's also the exact entanglement cost of a sequential simulation. And the sequential simulations in general have a higher cost because they include parallel simulations as a special case. Okay, so there are applications of these observations, one of which is that this operational task of exact entanglement cost is additive, the optimal rate. The exact entanglement cost is not convex, it's not monogamous. So that tells us something about the structure of entanglement, that these properties are not necessarily required. The other application is we can, since we've solved the exact entanglement cost of states and channels under PPT operations, because the PPT operations include the LSCC ones, all of these, the kappa entanglement is always a lower bound on the exact LOCC entanglement cost. So that's the one of actual physical interest. And there are special channels that we call resource feasible, for which the entanglement cost, the non-exact one, that one is equal to the entanglement cost of a resource state. And so it's somehow simpler to just calculate entanglement cost for a resource state. Okay. And then the final application that we discussed was solving the entanglement cost of basic quantum channel models. Okay, open questions. I guess I delivered this talk at SQuInT a while ago. I don't know if these have been addressed. I think for sure the second one has not been addressed. But there's a question of whether the exact entanglement cost is, when you have LOCC operations, whether that's additive. That's an interesting question. Another question that arose when we were analyzing Gaussian channels. In general, Gaussian channels, they're described by essentially two matrices. One is a scaling matrix, another is a noise matrix. You can look at the reference I'm giving as a book of Alessio Serafini on continuous quantum variables or Gaussian quantum information. So there's a question whether there would be this formula for the exact PPT entanglement cost of a Gaussian quantum channel. We really think that this is the case. There's a quantity called log negativity of a quantum channel. This formula was given in a paper of Nicolas Serf, and we strongly suspect that this formula will be the same for the exact PPT entanglement cost. Okay. And more generally, there are questions about the resource theory of quantum channels and a resource theory of entanglement for quantum channels. After I gave this talk, Xin and I and Siddharth Das and Stefan Boimel, we posted a paper to the archive about entanglement theory of bipartite channels. And then around the same time, Gilad Gur and his collaborator, Carlo, I believe is his name, they posted a paper about similar concepts. So you can read about these extensions there. Okay, That's all I had to say. If you're interested in more details or more of the references, you can look at this paper that I wrote with Xin and this paper that I wrote about entanglement cost. Thank you very much.